first of all, let me thank Mohammed and Amrit and everyone, Asif, for asking me to give a short talk or tutorial on symmetry-based recoupling, which for me is a subject that I've barely thought about for many years. So it's been a bit of a learning experience just for myself, actually, to remind myself of these things. Our group for the last 10-15 years maybe has been mainly doing solution NMR. So it's good to have a bit of a refresher actually in some of these topics in solid state NMR. So I haven't prepared anything very formal, so this is not going to be a very formal talk. I will just make some drawings on the whiteboard here, on the tablet, refer to a few papers now and again, and please feel very free to interrupt and ask questions as I go along, so that will help me understand, which points need more emphasis or explanation. So I thought I'd start by just giving some little introduction to solid state NMR. I don't know how many of you in the audience are exposed to solid state NMR. Very often NMR people are mainly exposed to solution NMR to start with, although that has changed a lot. But just to introduce the topic, I'm just going to pick up this article here from these three gentlemen. One of them is Alexei Yershov, who is a visiting professor in before the pandemic, at least before Southampton, before the pandemic in Southampton. He and his co-workers here wrote a very, very nice article back in 2002, which I recommend to you. It's a very good overview of solid state NMR and some of the problems methodological problems in solid state NMR at that time. And it starts off in a very appropriate way by showing a couple of NMR spectra. One is on the left here. This is a solution carbon-13 NMR spectrum of one carbon-13 labeled glycine in solution. Let's just remind ourselves what glycine is. It's the simplest amino acid. It has this structure like this. So this is glycine. And the substance we're talking about is labeled with carbon-13 at this position number 1. So the solution NMR spectrum of one labeled glycine has a strong peak at the labeled position, the CO position here. It has a second carbon-13 peak over here, which is actually from the natural abundance molecules. About 1% of them also have a carbon-13 in the second position. So they give a peak at a different chemical shift, a much lower chemical shift over here. And then you see this splitting structure, which actually comes from the spin-spin couplings, the J couplings between the carbon-13s and each other, and also the carbon-13s and the two protons here. So, for example, this peak here is a triplet that comes from the coupling to the protons, and each component of the triplet is split into two because of the coupling to the other carbon-13. So that's solution NMR. We get a very nice narrow NMR spectrum with clearly resolved chemical shifts telling you about chemical identity, and also some spin-spin couplings which tell you about how the atoms in which the nuclei are contained are bonded to each other. By contrast, a solid state NMR spectrum of crystalline 1 carbon-13 glycine. Actually, both of these materials are the labeling level is 10%. Yeah, So that's why there are 10 times more molecules with a carbon-13 in the CO position than there are in the C alpha position. Anyway, the same substance, before it's dissolved in solution as a powder, is just basically an uninformative hump. Actually, it's maybe just possible to see some sort of broad feature from the C alpha, the C2 site, and this strong feature from the labeled C1 site. But basically the spectra are very broad and generally uninformative. And so a long time, for a long time in NMR, probably until the 70s, 1970s or so, solution NMR was actually called high resolution NMR because of its narrow lines, and broad line NMR referred to solid state NMR. So in other words, the very broad lines observed in a solid state were regarded as somehow an intrinsic feature of solid state NMR which you couldn't do anything about. Now that situation changed, of course, with the development of two methods. So if we start with sort of solid state NMR, it started before the 1970s approximately. The lines were very broad and uninformative, and a lot of solid state NMR was concerned with measurement of relaxation times and things like that, or more exotic phenomena going on in metals and semiconductors and so on. Let's say the chemical applications of solid state NMR really only took off when there were two key methods, or actually ranges of methods were developed. One is, I'm sure you will all have heard of, called magic angle spinning, which involves putting the solid sample in a little ceramic tube called a rotor. So this would be a powder, which is then spun mechanically at a high frequency. Spinning frequency is usually called omega r, at a certain angle with respect to the magnetic field. So if the magnetic field is in this direction along the z-axis in this frame here, this special angle here is technically it's the inverse tangent of root 2, which is approximately 54.7 degrees. It's called a magic angle because when the phenomenon was described in which this rotation of the sample narrowed the NMR lines, somebody humorously pointed out it was the angle was magic, and then since then it was called the magic angle. So it's a very carefully chosen angle, which is there for a well-known reason, of course, but I probably won't go into those technicalities. And this causes a strong narrowing effect of the NMR spectrum. So that was one move towards getting chemically informative, high-resolution spectra in the solid state. A related development is what's called multiple pulse decoupling or dipolar decoupling, which was the development of complicated pulse sequences which are applied to a static sample. So basically, for magic angle spinning, you rotate the sample but don't apply any radio frequency fields. In these dipolar decoupling experiments, you don't rotate the sample, but you apply radio frequency fields to the sample with complicated modulations. So radio frequency fields applied to the sample while the sample is static. And these two methodological advances, they both of them, to within certain approximations, eliminate some of the interactions which cause the broadening of NMR spectra. So as we'll see, we'll look at this in a bit more closely in a minute. The magic angle spinning averages out what's called the chemical shift anisotropy interaction, and also averages out the dipole-dipole interaction. These are interactions which are not important, at least for line positions in solution NMR, but which cause this very strong broadening in solid-state NMR. The dipolar decoupling sequences, the earliest one and the most famous one goes under the name of Wahuha, from its authors Waugh, Huber and Haberlin. And then there's a whole family of others, MRev8, Lee Goldberg, and so on. At one time, the solid-state NMR world was just flooded with lots and lots of pulse sequences of increasing length and with increasingly nice properties. These dipolar decoupling sequences are designed to eliminate the dipole-dipole interactions between spins. But they don't eliminate the chemical shift anisotropy, so one of the motivations for that is to study chemical shift anisotropies, for example. So we have these two contrasting methods: magic angle spinning, which spins the sample but doesn't apply radio frequency fields, and dipolar decoupling, which applies radio frequency fields but doesn't spin the sample. The recoupling experiments, which started to take off in the 1980s and 1990s, evolved from asking a natural question, which is what happens if you do both of these two things at the same time? And in particular, how do you arrange some type of synchronization between the rotation of the sample and the application of periodic radio frequency pulse sequences in such a way that you get a desirable effect? It was already starting to become realized that if you applied dipolar decoupling but rotated the sample, then that would interfere with the operation of these sequences. And similarly, if you did magic angle spinning but then started to apply pulses, then that would interfere with the operation of the magic angle spinning. So there was a lot of work on sort of why does that happen, how can you stop it happening, and the problem of how do you arrange some type of synchronization of these two worlds together so that you can get the effect you want. And the main motivation here, and why it's called recoupling, is as follows, is that if you do magic angle spinning, which is essential for gaining high resolution spectra in solids, you remove the chemical shift anisotropy, which is the main thing which is responsible for the broadening of solid state NMR spectra usually. But you also remove the dipole-dipole coupling. Now in many cases that's desirable as well. However, those dipole-dipole couplings can be really interesting for you because they depend on distances between nuclei. So the dipole-dipole interactions between nuclei are of the order of the distance to the inverse third power, the inverse cube of the distance between nuclei, multiplied by well-known physical constants. So if you can measure the dipole-dipole coupling, then you can measure distances. And indeed, in solution NMR, that's the basis of powerful techniques such as the nuclear Overhauser effect, NOSI spectroscopy, for example. But in solid-state NMR, there was this basic problem that if you do magic angle spinning, you remove chemical shift anisotropy and the dipole-dipole coupling. For the most part, you want to get rid of the chemical shift anisotropy, but then if you also get rid of the dipole-dipole coupling, you've lost this geometrical information on the distances between nuclei. So one of the basic problems, in fact there's a whole class of problems related to this, but one of the basic problems is how do you remove the chemical shift anisotropy so you get high resolution while not removing the dipole-dipole coupling. And you can't do that actually by just spinning the sample. You can't do that by just applying radio frequency fields without spinning the sample. But you can do it within approximations by both spinning the sample and applying suitably synchronized radio frequency fields. And there was a flourishing of different methods for achieving these types of effects. Some of them go under the name of REDOR was one of the earliest ones, and in fact one of the best ones, and is still one of the most robust and reliable methods. That actually lets you measure heteronuclear dipole-dipole couplings. And for homonuclear couplings, there was a whole forest of sequences with dramatic names like drama and so on. There was a large sort of flora of these sequences, but what at that time in the early 2000s, I think it's fair to say, in the 1990s or so, there was a bit of lack of general principles about how to arrange these two operations together in such a way that you could predict, at least approximately, how a pulse sequence should be designed and how it should work. And this, the need for some type of general principle was at least partially solved by the development of symmetry-based recoupling, which allows you to construct sequences based on some relatively simple symmetry rules. And those are the rules that I would like to try to explain to you a bit. So again, so the basic problem then is, if we go back to Alexei Yershov's article here, if we scroll through it, there's good sections on the different types of solid-state NMR. So, for example, here we have this is some small peptide here with two amino acids joined together with magic angle spinning and some other related techniques, cross-polarization to enhance the carbon-13 magnetization, proton decoupling. One can get sort of good solution-like carbon-13 Nmr spectra, which start to approach the quality of solution NMR, but without the huge broadening that you normally get in solid-state NMR. But as explained, that effect comes at the expense of removing the dipole-dipole couplings, which are often the source of important structural information. And the problem of how to recover the dipole-dipole couplings in the presence of magic angle spinning is one of the variety of problems that the field of symmetry-based recoupling tried to address. So let me try to move on to explain how the way more or less to think about this problem. Let me just do that. And a good place to start is a little table, which I often use. Mohammed will be very familiar, I think, with this table. So the table there's many varieties of this table actually, which are increasingly sophisticated. But the basic one is to start with listing some different nuclear spin interactions. So we have, for example, the J coupling. We have the isotropic part of the chemical shift. We have the chemical shift anisotropy. And we have dipole-dipole couplings. Now those are going to be the rows of our table. There are actually a few more exotic ones, which we're not going to bother about here. And then we're going to make a table with a column of the columns are going to be 3 different numbers, which I'm just going to label as space, spin, and field. Just get that out of the way. And the numbers in the table express the rotational properties of the different interactions. Under spatial rotations, that means actually changing physically the orientation of the molecules. So, for example, by rotating the sample. So if you look at the chemical shift anisotropy, for example, here I put a number 2, here I put a number 1, and here I put a number 1. Now, these numbers here are technically the rank of spherical tensors. But rather than get into the technicalities of it, let me just make an analogy with atomic theory. So if it's a 2, then it means it looks like a d orbital, which most of you will know from atomic theory in chemistry or physics. If it looks like a 1, then if it's a 1, then it looks like a p orbital. And if it's a 0, it looks like an s orbital, which is spherically symmetric. So what this row here is saying that the chemical shift anisotropy interaction, if you rotate the sample bodily in space by mechanical rotation, then it behaves like a d orbital. So for example, if you rotate by 180 degrees, then nothing happens because you always just exchange the signs of the orbital with each other. If you rotate by 90 degrees, then you actually change the sign because you bring this plus here where the minus was before. So that's how d orbitals behave. If we sketch d orbital actually a bit more closely, like this, between the positive and negative lobes there's a line, and that line actually subtends the magic angle. That's 54.7 degrees. And just for your interest, as a matter of interest, those of you who are, at least those who are in Europe or most parts of the world, we use A4 paper all the time. If you take a sheet of A4 paper and arrange it in this way, and then draw a diagonal, then the angle between the diagonal and the short edge is the magic angle, 54.7 degrees. Okay, so the row in this table says the chemical shift anisotropy behaves like a d orbital with respect to rotations in space. If we rotate the spins but without moving the molecules, so that can be done by applying radio frequency fields, it behaves like a p orbital. And this last column is more exotic actually, and is more or less entered here for completeness, because this is a manipulation which in ordinary NMR we can't do, which would be to rotate the magnetic field while keeping the molecules fixed in space and not rotating the spins. So, but for completeness, that would complete the picture of the interaction, which involves all three of these things. The chemical shift anisotropy interaction actually behaves like a p orbital with respect to rotations of the main magnetic field. And we can write these signatures, so these are called rotational signatures. For all of the common homonuclear interactions. So the J coupling is actually 0, 0, 0. It doesn't depend on the orientation of the molecules, and if you apply fields to the spins, then it does not effectively change the interaction. The isotropic chemical shift is 0 for space, 1 for spin, and 1 for field. And the dipole-dipole coupling is 2 for space and 2 for spins and 0 for field. So there's a lot of NMR in this table here, actually. And I excuse me a minute. Yeah, I direct you to this review article on symmetry-based pulse sequences, and basically I start off by listing these rotational signatures, and there you see the same table as I just sketched out. And yeah, we'll need these numbers. So the space rank is called L, and the spin rank is called lambda in this notation. So let me put that on the table as well. So the space is L and spin is lambda. So this table tells you actually how interactions transform when you do different types of rotations, either of rotating the sample bodily in space, which you do in magic angle spinning, or rotating the spin operators as you do when you apply radio frequency pulse sequences. Now, in solution NMR, in isotropic solutions, so not liquid crystals, but isotropic solutions, the molecules tumble rapidly, and that averages out every interaction which does not have a zero here. So if we're doing solution NMR, whoops. Then we have the J couplings and we have the isotropic chemical shifts, but we don't have the chemical shift anisotropy because the tumbling of the molecules averages out anything which does not behave like an s orbital, so have rank 0. And that's why you get high resolution NMR in solution, because you've removed these large anisotropic interactions, leaving only these usually much smaller isotropic interactions. So I'm not going to do any theory seriously, but basically the theory of symmetry-based recoupling starts by taking the spin Hamiltonian, which expresses all of the interactions between the nuclear spins in the sample, and expressing it as a sum over all the interactions. So you usually conventionally use capital lambda for all the different interactions. And then for each interaction, it's a sum over the spatial components, and to sum over all the spin components of some complicated term which belongs to each interaction and then takes 4 different indices. And the way this always works, since we're doing here spherical components, is that if you have a spherical tensor of rank L, it always has two L plus 1 components with an index m, which go from minus L to plus L. So, for example, the dipole-dipole coupling has space rank 2, and it has spin rank 2 as well, and it has a set of components given by m and mu. So we'd have HDD is the sum where m goes from minus 2 to plus 2 in steps of 1, and mu goes from minus 2 to plus 2 in steps of 1 as well. So that would be 25 components, 5 times 5, so 5 space components, and for each of those 5 spin components. So just one single interaction actually has 25 terms in it. Similarly, the chemical shift anisotropy has 5 space components, 2L plus 1, going from minus 2 to plus 2, and then the spin components go from minus 1 to plus 1. So we have 5 times 3, we have 15 components for the CSA, and so on. And part of the difficulties in the field was and remains so is that there's an enormous number of terms to keep track of. So the aim of symmetry-based recoupling, really, the symmetry-based theory, is to develop some symmetry theorems which allow one to keep track of these terms and actually set them to 0, the ones we don't want, just using symmetry rules but without any detailed calculations. And that gives a very good start.
If I can interrupt, Malcolm.
Yeah.
We have actually a question.
Okay.
From David Bryce, which you and I are going to love.
Okay.
And he asks, I suppose the rotational numbers for J are for only the isotropic part of the J tensor, and the anisotropic part of J is lumped in with the DD part.
Yes, that's right, David. As you, I'm sure you're very extremely aware, is that this is slightly oversimplified. So this is just the isotropic part of the J coupling. But there are in fact 2 more terms: the antisymmetric term, which we tend to call in our group J1, and the anisotropic term, which in our group we call J2. This one we call J0. But this is sort of a bit of a private notation, but it's maybe less clumsy than talking about antisymmetries and symmetrical traceless components and so on. So these are exotic additional terms which are normally of very little importance, but just for completeness, the J1 term is actually 1, 1, 0, and the J2 term is 2, 2, 0, which has the same symmetry as the dipole-dipole coupling term. So this is usually lumped together. And since J2 is usually considerably smaller than the DD term, then normally it can be ignored. But in more careful work, as like yours, David, then one should really distinguish these 2 terms. So I've oversimplified the picture here a little bit. Is that okay?
Okay. I think we can move on. We have only one other question, which I think you've already answered.
Okay.
which is by Roman Picasso-Frutos. You have explained that with decoupling pulse sequences and MAS, we can do solid state NMR with lines with broadenings comparable to liquid state NMR. What are then the advantages of solid state NMR over liquid state NMR?
Well, you can study solids.
And we've just gotten another question.
Yeah.
By an anonymous attendee. If we start rotating the B field,
Yeah.
will the CSA have 5 times 3 times 3 equals 30 components? I think the math there is wrong, actually.
Well, okay, yeah. Well, yeah, 5 times 3 times 3, right? So what the hell is that? I don't know.
I think
5
it's not
times
30.
Yeah, it's not 30, whatever it is. 5 times 3 is 15, so 15 times 3, 45 maybe?
Yeah.
Yeah, in principle that's true. That's true, yeah. Although there are technical issues there. But in principle that's true. But so far, I don't think anyone has seriously extended this to actual physical rotations of the magnetic field, but who knows, maybe we will get there. We are actually doing some work preparing those sort of experiments actually, but nothing ready to talk about right now. Right, so normally the magnetic field is fixed in direction, and then we're only worried about the spatial and the spin rotations. Right, so we have a hell of a lot of terms to worry about. So let's just take a particular example, because it was maybe the earliest and the best example of this type of technique, which is that some of the terms, so you can see actually this table is maybe a bit simplified, because although this gives the rank and of the space and the spin components within each component here, or each term here, there's a large number of subterms, if you like, with different quantum numbers m and quantum numbers mu, which run from minus lambda to plus lambda in that case. So within this forest of terms here, there might be a couple which are really interesting. So, for example, these were the target of one of the earliest examples of this technique. And the main thing about this is that so this is the mu quantum number here is 2. And that means it's a double quantum term. So what that means, and then you have a complementary term on the other side in which has a -2 quantum, and it's associated actually with a spatial component with an opposite value of the m quantum number, which in this case is -1, and for the other one it's +1. So one can start by asking the question: how could one design this synchronized set of sample rotations and radio frequency pulses in such a way that you can get rid of all the 23 other terms while only retaining these 2 terms, at least within some level of approximation? So, one way of doing it might be to actually calculate explicitly what all of these terms are for a given pulse sequence under a certain rotation of the sample, and develop a set of simultaneous equations, and try somehow to solve them in order to get rid of the terms you don't want and retaining only the ones you want. And that might be feasible, but it's very difficult. But the symmetry trick actually lets one solve this problem sort of more or less at a stroke, at least to the first order approximation. So let me try to explain how this works. The motivation is, why would one want to do that? So what's interesting about the double quantum term? Well, double quantum filtering is a very powerful technique in solution NMR, but also in solid state NMR, since it lets you really simplify spectra. For example, pick out pairs of spins which are close to each other, while suppressing isolated spins. And that can be very useful actually in many different techniques for getting information on molecular structures. So there's a strong motivation for actually exciting double quantum coherence in solids. And indeed, nowadays, these double quantum solid state NMR sequences are some of the best ones for solving biomolecular structures, for example. So that's the motivation, but now the question is how to do it. It's difficult. The way this problem was solved was to set up some symmetries. So I'm not going to go into theory, but let me just sketch out at least some of the theoretical concepts. So we have the magic angle spinning rotor, which is rotating with respect to the magnetic field. And in the theory in solid state NMR generally, the way one proceeds is to define some reference frames. And the first reference frame to define is one in which the magnetic field is defined to be along the z-axis of that reference frame. And we call that reference frame the L frame, or the laboratory reference frame. And now we have a sample holder. The sample is packed in as a powder. And we can define another reference frame which is fixed to this rotor. So let's call that the rotor reference frame. It has a z-axis along the rotor. So as the sample rotates, then the orientation of the R frame in space changes in time. And we express the relationship between two reference frames using a mathematical object called set of Euler Angles, which is usually denoted RL, big omega RL. And since the sample is rotating, that's time dependent. So these are called Euler Angles, and I'm not going to go into the definition of what these angles are. But it enables you to express the orientation of two three-dimensional objects with respect to each other, and it's one of the essential tools in the theory of solid-state NMR, or indeed in a great deal of NMR, including relaxation theory as well. So for a rotating object, an object which is rotating at a fixed frequency about a fixed axis, these angles are actually quite simple. They have the form of so this is a set of angles which actually is composed of three angles called alpha, beta, gamma. the alpha angle depends linearly on time, is proportional to time multiplied by rotation frequency. And technically there's a negative sign, but let's not spend any time over that. And actually the gamma angle doesn't really matter, so I'm just going to set it to 0. The beta angle here, this is the angle between the rotor axis and the field. So for ideal magic angle spinning, this would be the magic angle, the inverse tangent of root 2. So that equation there describes the rotation of the sample in space. Okay, now we have to think about the radio frequency fields that are applied. So one has some complicated pulse sequence in time. And without going into detail, the applied resonant radio frequency fields rotate the spins. They induce a rotation of the spin states in time, which we can call omega RF for the rotation induced by the radio frequency field. And that can be very complicated because the pulse sequence can be complicated, and actually the 3 Euler angles which describe that rotation are not, in most cases, are not immediately obvious to go from the pulse sequence to these Euler angles, which are time dependent. It's not immediately obvious, but it can be done. So this is a bit of an indirect path of how to go from a pulse sequence to the Euler angles. But you can, given a pulse sequence, you can derive these Euler angles, and furthermore, if you want a certain set of Euler angles, you can figure out which pulse sequence to apply. And actually that's part of the technique in developing symmetry-based recoupling sequences. So there is a one-to-one correspondence, even if it's not the most direct one, but it's a route that one knows how to follow to go from a pulse sequence to the Euler angles. And the let me just sketch through the theory here, make sure I get this correct. What one sets up is certain symmetry relationships. So there's two classes of symmetries which have been discovered. There may well be more, but to my knowledge nobody has really worked on this since mainly our group sort of got onto other things, but it's certainly true that these arrangements are not unique by any means. But the arrangements which were discovered may be best shown by a diagram. So there's two main classes of sequences which are called C sequences. And the C sequences, one normally uses this notation. So one says C and then 3 numbers which are called symmetry numbers. There's big N, there's small n, and there's nu. And so if one has a certain sequence here with 3 different symmetry numbers, this is constructed in the following way. One starts with some set of radio frequency fields which is called a cycle, which means that just over that element here all spin states are returned within the usual approximations back to their initial condition. So for example, a 2 pi pulse rotates all spins, at least within a phase factor, back to their initial condition. or 180x, 180 minus x. Also rotates the spins one way and then rotates the spins back again the other way. So the symmetry theorems only require that this cycle, this element, behaves like a cycle. So it gives a net rotation of 0, or more generally an integer number of 2 pi. Within that requirement, there's complete freedom. So one starts with a cycle and then repeats it big N times, but with a phase shift. And the phase shift is derived by taking the symmetry number nu, multiplying it by 360 degrees, or 2 pi, and dividing it by n. So what that means actually is that if you clock out the radio frequency phases, is that the sequence is repeated n times, but the phases increment and will have completed new full revolutions by the time you've finished. So I think there's a diagram here which maybe makes that a bit easier. So one should look at this part of the diagram here. So this diagram here is for the sequence C721. So the 7 means that there are n cycles, 1, 2, 3, 4, 5, 6, and I think the 7th is somehow hidden because it's just sort of obscure there. 1, 2, 3, 4, 5, 6. No, sorry, I miscounted. 1, 2, 3, 4, 5, 6, 7. 7 cycles. The phase is denoted by turning the handle around the axis here. And if one looks, since nu is 1, it means the phase goes through 1 revolution here. So one arranges the radio frequency phase to go through that type of arrangement. In this case here, in the lower diagram here, this is C1445. So there are 14 repeated cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and probably I missed one. Should be 14. But by the time one has finished all 14, the phase has gone through 5 revolutions. So that's how one arranges the phases of the radio frequency fields. But we also have to synchronize with the sample rotation. And the trick is to make sure that those n, capital N, cycles are completed in just the amount of time taken for the sample to revolve n, small n, times. So here, in the sequence C721, so there are 7 repeated pulse sequences with phases going through 1 revolution in the same time as it takes the sample to revolve twice. Similarly,
I can interrupt Malcolm
yeah,
with a couple of questions which are relevant.
Yeah.
Quintana Reynard Fetus asks, why is the chosen number for the sequence 7 or 14?
Well, I'm going to try and come on to that. So here I'm just saying, so how are these numbers? So right now I'm just describing what the sequences are, and what they do is going to come in a minute. But if you just accept for now that these numbers are as described, I'm just describing, saying if a sequence has this symmetry, C721, what does it look like? And then afterwards we're going to discuss what do these numbers actually, what effect do they give rise to? Is that okay?
Oh yeah.
Is that is he okay with that?
Oh yeah, he said thanks.
He says thanks.
So yeah,
okay.
we can move on. We have other questions, but maybe you can save them after the discussion.
Okay. Right. So that's basically the arrangement of radio frequency phases. This spiral of phases. So the nu number is the number of revolutions of the phase. That's called the spin winding number. And the n number is the number of revolutions of the rotor, which happens in exactly the same time. So when performing these sequences, one must arrange the timing so that that happens. So if one knows the rotation frequency of the sample, one knows how long it takes for a one period. So then one can arrange, in this case, that 2 complete sample revolutions are just finished just at the time when 1 phase revolution has happened. So that's called the space winding number is small n. Okay, so that's the definition of the C sequences. There are also R sequences which have a slightly different construction, but let me maybe come back to them if there's time. But there's a similar sort of arrangement, but this time involving pi pulses rather than, or 180-degree rotations rather than 360-degree rotations. And there may well be other, as yet unknown, symmetry arrangements. Now, okay, so let's get on to the question though. So that's so that's how a C sequence is defined. So, for example, just to go through it again, C721 requires that we apply 1, 2, 3, 4, 5, 6, 7 C cycles. So each of these elements may itself be some set of radio frequency fields, but the main thing is that it's a cycle. It gives a 2 pi or a multiple of 2 pi rotation for the spins. And then the phases are incremented in steps of, so if this is a 0-degree phase, the next phase is 360 times 1 over 7, which is about 51 degrees if I remember. And then 360 times 1/7 times 2 will be the next phase, and so on. So one increments the phase in the steps of this 51 point something degrees, and one arranges that so this sevenfold repetition of the sequence is matched to exactly two rotations of the sample, if tau r is the rotation period. So that would be an example. And how do we figure out what it does? So it can be shown. And I won't go into the technicalities of it, that this symmetry leads to selection rules. Which is where selection rules come from in all forms of spectroscopy. Selection rules are always related to some symmetry in the interaction. And the selection rules are made are very concise. So we have these Hamiltonian terms. So let me use the blue means the space part, and then the red means the spin part. And then we have a certain interaction, big lambda. And we're operating within an approximation, in an approximate theory which is called average Hamiltonian theory. And the selection rules apply to what's called the first order average Hamiltonian, which is this sort of first order approximation to how the sequence operates. And one of the complications of these sequences, why things are not, totally solved by this, is that the first order approximation is very often not sufficient. But nevertheless, it's a starting point. So these are selection rules on the first order average Hamiltonian, the first rough approximation of how a pulse sequence actually operates in a realistic context. And the selection rules are very simple to write down, actually. It says that this particular contribution to the average Hamiltonian from terms with certain space quantum numbers and spin quantum numbers vanishes if a certain inequality is not satisfied, which is that, which is m. So the m component times the n winding number minus the mu component of the interaction times the spin winding number is not equal to an integer multiple of big N. And usually the symbol here Z is used to mean any integer. So that's the selection rule. So in principle then, for all the 25 components, for example, of the dipole-dipole interaction, and for a given choice of numbers here, one could go through them one by one and then figure out which of them are symmetry allowed according to this selection rule and which of them are symmetry forbidden. And indeed, one can write Mathematica code, and that Mathematica code, for example, is available, which allows one to do that. It tells you immediately which terms are symmetry allowed under a certain symmetry. But there's actually another way of doing it just by a diagram, and that's an easier, that's maybe a more attractive way of doing it. So these are called space spin selection diagrams. And it goes as follows. So you, so let's suppose we're interested in the dipole-dipole interaction. And to remind you, then we have space rank L is 2 and spin rank mu is 2 as well. So one starts by splitting up. I'm going to just splitting up these, drawing a ladder of terms which are split up as follows. So we're going to have the, we split up the m components, so m goes from minus the space rank to plus the space rank. As follows. Now I've drawn wide gaps here because the rule is, to make this diagram up, is that you space these components by the number n. which, if we're interested in the sequence C721, then we have n is 2 and mu is 1. So we draw a grid where these are split apart in steps of 2. Now, in general, actually, there's a 0 component as well, but if we're doing exact magic angle spinning, that term actually vanishes. If we're spinning but not at the magic angle, then we would have a 0 component as well. But for magic angle spinning, we can actually remove immediately the 0 component here. Okay, so those are the 5 space components, going from m is -2 up to +2, for L is 2. And now for each of those, we have a spin component. And the rule is we now split those up by nu in steps of nu, the spin winding number, which in this case is 1. Right, so let's do that. So then this one splits up into 5. To be a bit careful about this. It's maybe easier to do if you have a real grid to work with. So actually, if I got that right, that comes on the same level as this one, which now splits up into 5 as well. And the same on the other side. So this would be mu is -2 here. So this line here, if we follow it through, is the spatial component +1, m is +1, and the spin component mu is -2. So that's one of those double quantum terms that we were interested in. But there's all these as well, and the same on the other side. In fact, from the other side, there's going to be another term here with mu is -1. M is -1, and mu is +2. So another double quantum term. So those are the 2 terms which we wanted to select. But there's 23 other terms. And this is where the selection rule comes in, because we haven't talked yet about the number big N, 7. And the way the selection rule works is, the way to visualize it is you erect a barrier here with holes. So let me try and sketch the barrier. And actually the barrier has holes which are equally spaced and go off to ± infinity. But the spacing between these holes is big N. And basically a term is symmetry allowed only if it passes through a hole in the barrier. So the barrier is, for the C sequences actually, the barrier is organized so that the level 0 is always at a hole. So that's here. Where's the next hole? Is 1, 2, 3, 4, 5, 6, 7. But there aren't any terms there. So all of these terms in between are blocked. And 7 is the smallest number which accomplishes that. So this symmetry, without doing any detailed calculations, suppresses, in the first order average Hamiltonian, all 23 terms, leaving only these 2 double quantum terms. And that enables double quantum hermenuclear recoupling. So in the article here, this diagram is shown. So this is the same diagram as I just drew, but drawn more neatly, of course, showing that the desirable term with mu is 2, double quantum term, is passes through the hole in the barrier. But the next hole in the barrier is 7 up, and which is just enough to suppress all the other terms. And if you draw the same diagram for the CSA, so the CSA also has L is 2, so a space rank of 2, but the spin rank is 1, so there's only 3 branches on each, there's only 3 twigs on each branch, so all of those are suppressed as well. And you can look at the property of isotropic shift as well. So this diagram actually can be used to show you that without doing any mathematics at all actually, that the C721 symmetry is sufficient to select out the terms of interest and suppress, at least in the first order approximation, all the ones you're not interested in. And this was the first. This was called at the time C7. Was developed actually before the sequence was generalized. The principles were generalized a little bit with the addition of these other symmetry numbers. This shows maybe a bit more clearly the sequence of phases: 0, 2 pi over 7, 4 pi over 7. And so on, and the position of the rotor as it goes around through 2 revolutions during the same time. Some demonstration data on double quantum filtering, and a set of curves showing as you increment, so this was done on a sample containing pairs of carbon-13s, that as one increments the duration of the sequence, one gets these oscillations which are due to the double quantum excitation of the spin pair. And the nice oscillations let you measure the dipole coupling between the nuclei and hence the internuclear distance with high precision. So that was the basic principle of the C sequences. So if I just go back, with this selection rule here, let me just dig out the selection rules. Yeah. So here you see again the selection rule for C sequences, which can be translated into the space spin selection diagrams. There's another set of sequences based on slightly different principles, but small modification. Uses basic elements which are a 180-degree pulse rather than a 360. And that gives rise to slightly different selection rules. So you can see the selection rule for R sequences is similar, but there's one major difference, which is it depends. So the selection rule for C sequences does not depend on the rank lambda. It only depends on the mu value. With R sequences, one can include an additional dependence on the rank lambda. And it works actually that this combination of the sequence numbers, the winding numbers n and mu, and the space quantum number m, and the spin quantum number mu, the selection rule relies on comparing that with the value of n, which is always an even number actually for R sequences. So it would be n over 2 multiplied by an integer. But the trick is that the integer now depends on the lambda of the value of the rank lambda. So basically, if the rank lambda is an odd number, then z is any odd integer. If lambda is an even number, then z is any even number. And that can also be expressed by a diagram. That's actually done here. So these are diagrams now for one of the R sequences, R1817. And if you look carefully at this diagram, you can see that the position of the holes in the barrier shifts depending on whether we have an odd or even rank interaction. So the dipole-dipole coupling has lambda is 2. That's even. So the holes are at an an even multiple of 9, which is a half of 18. So it starts at 0, and then you count up 9, and then you get to the next hole. While for the chemical shift anisotropy has a spin rank of lambda is 1, which is odd. So then the holes, actually I'd made a mistake in the, I just made a mistake. The hole is at 18. So n over 2 is 9, and the holes are at even multiples of 9, so 0, 2, and so on. So 0, and then twice 9, which is 18, and so on. Since here lambda is odd, then the holes are at plus minus 9, and then plus minus 3 times 9, and so on. But again, you can express the selection rule as a diagram and figure out which terms are allowed and which are not. And then you can use these theorems to figure out which symmetries give rise to certain desirable effects. And actually this article contains a series of tables which symmetries achieve certain effects which may be of interest. So if I just scroll through Scroll through to some of them. So here, table 5, there's a concept called gamma encoding, which at this point I'm going to skip over. But the important thing is it's homonuclear double quantum recoupling, in which the selected terms have L is 2, M is plus minus 1, lambda is 2, and mu is plus minus 2. And one can just let the computer search through all the sequences which select those terms and suppress everything else, except with the exception of some terms, like an isotropic chemical shift term here, for example. So in amongst them is C721, which is the one we just analysed and was actually the first one discovered. But you can see actually that there's a whole flora of possible combinations of symmetry numbers which have those properties. And for each of those, one could draw up one of those diagrams and show, through the same arguments as before, that only these two terms out of the 25 for the dipole-dipole coupling are symmetry allowed. And then there are other tasks one may be interested in. So table 6 is very similar actually, except now it's M is 2. So here there's M is plus minus 1. But you can do the same thing with M is plus minus 2. That gives a slightly different orientation dependence of the recoupling effect actually. And there's a certain number of symmetries which achieve that. Here's an experimental example of a double quantum experiment on a uniformly carbon-13 enriched amino acid, in which one has double quantum frequencies in the vertical direction and single quantum frequencies in the horizontal direction. And you get these nice correlations between the double quantum frequencies involving pairs of spins and the peaks in the single quantum dimension. And this actually now you can just then connect the sites with each other and walk through the molecular skeleton. One can do something similar with R symmetries. This one, R1421, is actually quite popular. Here we see some more, and these have mu is 0. So those are zero quantum terms. So there are certain contexts where one would like to achieve zero quantum recoupling. And that can be done using these symmetries. Actually, this is an example of a zero quantum correlated spectrum. And then, well, actually, I barely remember what any of these are. This is basically these symmetries remove everything in the first order average Hamiltonian apart from the J couplings. And there's a large number of possibilities there. The same for R sequences. And so on. There are some applications where one would like to recouple the CSA interactions. So get rid of the dipole-dipole couplings, but just retain the CSA interactions. And that can be arranged by some other combinations of symmetry numbers. So in general, these theorems they don't solve for you the precisely which sequence to use, but they give strong constraints which are very helpful in designing sequences. When it comes to actually choosing a practical sequence, then one has other constraints to think about, like how much power does the probe tolerate? How fast can you spin? How fast do you want to spin in order to achieve the effect you want? And these days, actually, you typically spin much faster than is done when these methods were originally developed. So there are many other constraints which come into the game when actually choosing a particular sequence. But I think maybe I've hopefully given you an idea of what the thinking behind these sequences is, and a basic picture of how the selection rules work. So I think I'll stop here actually, and just very happy to answer questions or to discuss further as you want.
Okay, thanks a lot, Malcolm, for that. That was an extremely enlightening talk. And actually, we've received a flurry of questions. We have 13 at the moment, many of which you've answered already to some extent. And the most popular question is actually by Brian Michael. You mentioned that the requirement for the individual C RF blocks is that they form a cycle, but that can be accomplished multiple ways. How do you choose the specific RF block to use?
Yeah, that's a really good question, and here one's getting into the tricky details. So there are a few guiding I think that's where it becomes a bit more than an art than a science, to be honest, but there are a few guiding things. So one thing to realize is that the symmetry theorems tell you which terms are suppressed and which terms are symmetry allowed, but what it doesn't tell you is how large the symmetry allowed terms are. So this selection rule on the board here tells you that a certain average Hamiltonian term goes to 0 if some conditions are not fulfilled. What it doesn't tell you is how large that term actually is if the condition, if the symmetry allows it. And usually you would like that term to be as large as possible. So there's a parameter called a scaling factor, which may be derived for each C or R sequence. Let me see if I just in this article yeah, so that, as I just said, the selection rules tell you which terms are symmetry forbidden, but they don't tell you what the magnitude is of the symmetry allowed terms. And that may be evaluated actually by figuring out some complicated integrals. So this is one of the possible formulae for a scaling factor. And there are programs which calculate that for you for particular sequences. So that's one. So calculating a scaling factor for a given choice of, say, a C sequence, and then ensuring that it's relatively large or doesn't vanish, would be one important criterion. Then the next criterion will be, can you actually physically realize that cycle? Because you have to fit the cycle into a certain time interval, and that requires that the radio frequency amplitude is sufficiently large that you can complete it. And that will depend on the spinning frequency, because the faster you spin, the shorter each sample rotation is. And if you're matching that to the pulse sequence, then the pulse sequences then have to become shorter. Unless you change the symmetry numbers, which you can do. So that's another criterion to take into account, is the to get an acceptable scaling factor and for the sequence itself to be practically realizable. And then you have various imperfections which always come into an experiment, and you want the sequence to be robust with respect to them. So, for example, the C7 sequence, which was originally developed, used the simplest, more or less the simplest possible choice of a C sequence, which was two 360-degree pulses. Yeah, so that's shown here. Each C element here is two pi pulses or 360-degree pulses of opposite phase. So the choice of two pulses of opposite phase ensures that any overall any misset in the radio frequency amplitude is the effect of that is cancelled out again at the end of every C element. So that's about the simplest thing you can do if you want to retain some sort of compensation for radio frequency field errors. But actually this sequence, the C7 sequence, didn't really become very popular until Niels Nielsen, who I was collaborating at the time, suggested using a different composite pulse in this C element, which actually has a 90-degree pulse permuted from one side to the other. And that became known as post C7. And that turns out to make the sequence more broadband and more robust to various other imperfections. These are things which can't be predicted from just the first order average Hamiltonian, which I've been discussing so far. So unfortunately there's no very simple answer to your question. The actual choice of a particular sequence is a mixture of some things you can predict, like scaling factors, constraints, experimental constraints, often to do with power handling of the probe, and a little bit of wizardry to do with experience of composite pulses and other types of sequences, which ones are more robust and compensated for various types of errors, all of which can be predicted to reasonably well now with suitable simulations, but for which it's probably not easy to give a very simple answer. So the way most people work, I guess, with these sequences is to basically use one which somebody else has already used. And I'm not sure how many people have really ventured off into the sort of hidden recesses of these tables of possible symmetries. There may be some real gems there, actually, which nobody's really come across yet. I know that our group didn't really explore an awful lot of these possibilities.
Okay, that was a nice answer, very comprehensive. And you also ended up answering another question, which was by an anonymous attendee: is post C7 related to C7?
Yes, it is. So it's just it's the same symmetry, but with a different choice of a C element.
Mm-hmm. Okay. And, we have a few questions we have to get through. So Leo Gordon asks, actually, is it from the calculation of the time-dependent Euler angles between the lab and rotating frames which affects the success of symmetry-based sequences via MAS instability?
I'm not sure if I... So it's talking about MAS instability. So, for example, in real experiments, then the spinning frequency fluctuates, and I think he's alluding to the potential problem, which is a very real problem, that these sequences require a precise synchronization between the sample rotation and the pulse sequence. Now, at the time these sequences were developed, then typically one was spinning around, I think 10 kilohertz was regarded as being very fast. So typically 7 kilohertz maybe. With rather large rotors, relatively speaking. And they were stable, and the spinning stability was often very good. So it was possible to arrange these relative timings. Now I think there is a problem that with the much faster spinning frequencies which are available now, exceeding even 100 kilohertz, that we're in a different world there, because there will be small fluctuations in the spinning speed. Well, if the sample has to complete 1,000 revolutions before you achieve some particular recoupling effect, then some small instability will have a large effect over those 1,000 rotations. And I think that is a real problem. I think that's one of the reasons that the symmetry-based sequences are not, to my knowledge, employed very successfully in combination with very fast spinning. It's a problem which is possibly not beyond being addressed by technical improvements. So, for example, it should be feasible to detect the position of the rotor in real time as the rotor rotates, and then synchronize with that, not just by changing the timing of the sequence, but actually physically feeding back the timing to the pulse sequence, so as to make sure that the pulses land just when the rotor comes round and completed its circuit, for example. I suspect that that's technically possible, but I don't think that's actually accomplished on modern spectrometers at the moment. In the old days, back when I was working with solid-state NMR and myself learning about solid-state NMR, then there were such synchronization experiments performed just by having a mark on the rotor. But then the spinning frequencies were much slower, and it was much easier to do. In fact, the only piece of electronic hardware that I only ever attempted to construct with my own hands was actually designed to do that, and basically failed, so I've stuck to theory ever since, basically.
Yeah, that's a brilliant answer. And we have a few other questions. I don't think we'll have the time to go through all of them, but let's go through the most interesting. So Eddie asks, thanks for this talk. Using BABA, we can desynchronize the rotor with respect to T1 and model the spinning sidebands in F1 to get a distance. Can we apply this approach using these symmetry-based sequences to reach closer distances? Thank you.
That's actually a very interesting question. In fact, in this article, I think it's hard for me to answer that question immediately, but the BABA, B-A-B-A, is actually is discussed in this article. It's actually based on there's it's hard for me to give a brief answer. The diagrams which are drawn here, and they end up with a particular property, which means that for every spatial component, like here m is 1, there's only a single spin component which is symmetry allowed. mu is 2 in this case. Now you could imagine that if n was a smaller number, big N was a smaller number, there would be another hole somewhere here, and then there might be a second spatial spin component allowed for which still belonged to the same space component. So there wouldn't be a one-to-one correspondence between space and spin, but there would actually be, in that case, two-to-one correspondence. Now, if that happens, then you, for such sequences, then as you just said, the action of the pulse sequence depends on the time at which it's applied, and as you vary that time, you get a periodic modulation, which you can Fourier transform and get sidebands. Those sidebands are actually not caused by the dipolar coupling. They're caused by the fact that the pulse sequence varies in its operation as the sample rotates. It's quite a complicated topic, actually. So actually the answer to your question to some extent is the opposite of what you were expecting, so maybe, in the sense that for C7, for example, then it's arranged so there's only a single spatial component for every spin component, and then you don't get that modulation, which is actually a great advantage, because it means you can then apply the pulse sequence at any time. You don't have to worry about the synchronization. But it also means you don't get that type of sideband which you're talking about, which can be used to determine distances. Although I have to say, I remember when I used to sort of work in this field, that to me that seemed to be a very strange way of determining a distance, because the sidebands which one is observing are not actually caused by the interaction that one is trying to measure. They're caused by the pulse sequence not having an operation which depends on its angle, on the angle of the rotor with respect to the field, and only has an indirect relationship with the dipole-dipole coupling. It's a very hard thing to explain, but you might want to look at this particular review article, because somewhere in here then I think there is a discussion of that. Yeah, so this section here describes the operation of bar-bar, but using the sort of symmetry language. So what we're talking here, what I was talking about here, is sort of explained here, that the absence of gamma encoding, which is this relationship where you have a one-to-one relationship between space and spin, causes these modulations, which may be analyzed to estimate distances. And that effect actually disappears when you use the symmetries, which do cause this gamma encoding property.
Okay, we have a few other questions. So one which was asked by, oh, Eddie says thank you for the answer, by the way. But Quentin Reynard Feitas asks, what is the main difference in terms of interest between DQ, SQ, and ZQ, DQ correlations?
What is the main, can you repeat?
Yeah, what is the main difference in terms of interest between double quantum, single quantum, and zero quantum, double quantum correlations?
Right, so do you mean in terms of what you use those things for, what the applications of those are? Is that the...
Quentin, you can elaborate if you'd like.
Yeah, why don't you maybe turn your mic on or something? And
yeah, I'll allow him to speak, actually. So Quentin, you should be allowed to speak now.
Yeah. Can you hear me?
Yep, yep.
Yep. Yes, so my question is turning on the potential application. Why, for example, if I'm working on some materials and I use symmetry-based sequences, why should I use zero quantum, single quantum instead of double quantum, single quantum correlation, for example?
Okay, yeah, I get it. Yeah. Oh, you know what? I have some trouble remembering this actually. You can get correlation in both cases. Um, so I think there's examples in this paper here. So this one is a double quantum correlation experiment.
Mm-hmm.
There's another example. This one, which is actually single quantum correlation, but the mixing interval is zero quantum.
Okay.
Now, if I remember this, one of the things I remember is that if you have a zero quantum mixing Hamiltonian, for example, then the total magnetization is preserved, commutes with a zero quantum operator. Now, what that actually means is that if you have magnetization, let's say on one site in a molecule, and then you turn on a zero quantum Hamiltonian, then that can propagate to everywhere else in the molecule.
Okay, I see.
So you get a sort of total correlation spectroscopy effect, where everything is correlated with everything else, which can be useful in some cases. That's not true for double quantum. So the double quantum doesn't preserve the total magnetization. So I think you then tend to get maybe a more local, but more a sort of cleaner effect, in which it's more obvious exactly which spins are interacting with each other, and not indirectly through other spins. But I think it's best. I think that question really would be best answered by somebody who works with the practical applications of these sequences.
Okay. Thank you very much.
Thank you.
All right, so we're running out of time now, and while there are a few questions, many of them have already been answered. I think we'll just take the final free ones. So Yoav Shamir, for example, asks for table 5 shown from the paper, if all end up with the same non-zero components, what theoretical consideration should be taken into account when choosing which symmetry to use? And on a related note, Orlusky asks, how should I choose specific components of the interaction? I mean, how can I know which components yield which spectrum?
Yeah, so they're both difficult questions to answer. I think the first one I tried to answer, and maybe this article or other articles goes through in a bit more detail, that for particular C sequences, for particular symmetries, and a particular choice of C sequence, then one can calculate a scaling factor which tells you the magnitude of the symmetry allowed terms that one is interested in. And then there are instrumental constraints as well. So I realize that this is it's not satisfactory to some extent. It's only the start. The symmetry-based selection rules are only the start. They only give you a first step on the ladder. There's still a long way to go on the ladder, and in fact there's an infinite number of ladders to climb up. Because for each of these symbols here, there's an infinite number of C sequences to choose from. So this only provides a sort of framework which guides one's search for a sequence, and there are some general rules, and one usually starts by looking at work by similar groups. What did they use? That's how almost everybody operates. and hopefully you will find something appropriate. Unfortunately, that's not a very satisfactory answer, but it's about the best I can give, really. The other question was, which terms do you select? Well, I think again this article here does go through many of the possible applications of the symmetry-based recoupling and discusses what sort of effects you get by selecting certain terms. But the most popular ones are the double quantum recoupling sequences, and maybe the zero quantum. And some people have worked with the chemical shift anisotropy selection as well. So I think the question is best answered the other way around, really, is to say, what do you want to do? And then let's look at the problem. But maybe we don't really have time to go off on that tangent right now.
Oh yeah, and I think I'll take a very final question because this one is quite interesting. How can fast field sweep be incorporated in these rotational signatures?
No idea. I don't know. Field sweep.
Okay.
Yeah. Well, yeah. Why not? I think one would have to actually probably, well, either incorporate the effect of the field sweep is basically sort of part of a C sequence or a R sequence. It's another manipulation of the spins, so it should obey the same symmetry rules. But to my knowledge, nobody's done that. Could be nice. Yeah.
Okay, I think now we won't take any more questions. Someone asked, what's next in symmetry-based schemes? And another person asked a complicated thing about free spin, four spin approaches. But I think we won't have time to get through them. And for a more elaborate discussion, you can feel free to send us some emails.
Yeah, for the most part, I am very happy to try and answer emails, and I've enjoyed giving this little seminar and refreshing myself actually on a lot of these topics.